The CART training algorithm employs the classification and regression tree, is what it's named for. So classification and regression tree, CART, was developed to train decision trees, typically termed growing trees, right? So the procedure itself is very straightforward. The algorithm splits the data training set into two parts at every time using one feature K and a threshold. For example, like petal width is less than or equal to 2.5 centimeters. And it selects the feature and threshold by searching for a pair. So it finds a pair of K, which is a feature, and a threshold for K that yields the most homogeneous subset measured by the subset size. So what this looks like is we're going to start with the root node, and then each time we're going to split. So the root node splits into two, internal node split into two, internal node split into two, internal node split. And then sometimes you won't, sometimes it'll visualize where like if you don't have anything to the left or to the right, it will just drop the node, right? Keeps it clean, no point to show an empty node. That's why there's no leaf here. And then at the end, you'll have leaf nodes, and all of your samples have to end up in a leaf node. And that's our goal, is just to split it one at a time, so we get the most homogeneous subsets. So our objective function to minimize is J, which is our objective function of K, which is our class for our threshold of K is equal to M, which is the number on the left over the total number of samples we have times our Gini of our left plus M of our right over M Gini of our right. Right? And now the goal here is to minimize J, right? So get J as small as we can. We're going to test several J out for every step, and then we're going to take the one that minimizes it the most, and then we'll move forward. And if it wasn't clear, so G of left or right is the impurity on the left-right subset. And then M of left, right is the number of instances in the left-right subset. We're going to go FR subset. All right, so this process will halt when it reaches max depth. So max underscore depth, or any other number of hyperparameters that might stop it, right? You might say, I'm going to stop when all of my nodes have less than 2 samples or 3 samples. But you don't want to overfit because you don't want every leaf node to just have 1 sample, right? That would not make a lot of sense. So unlike the linear models that we've been talking about that assume a specific data structure, like a linear model or a polynomial or model, decision trees impose few assumptions on the initial data. And so if not properly constrained, they can erratically conform to the training set or overfit. The model is described, therefore, as non-parametric due to its lack of parameters, which it can have in abundance, but because the parameters are not predetermined at training, we still consider it to be a non-parametric model. So overfitting is a big problem in decision trees. as it is in all, but is a big issue here. And one of the reasons is just because decision trees are so easy to train that it's so easy to just keep going layer after layer after layer to get what you want. So to mitigate overfitting in decision trees, it's essential to control the model's freedom during training, and we call that regularization. I'm going to put that in blue because it's important. So regularization. And there's a number of ways that you can do that in sklearn. You can manage the max depth parameter. You can also manage things such as the minimum sample split, right? So how many samples are going each way, the minimum sample leaf, the minimum fraction leaf, the minimum leaf nodes, the maximum number of features. There's a number of things that you can do over and over and over here. And again, we need to be cognizant of this in decision trees because they're so easy to train. So let's take a look at two decision trees that we can train for the classic Moon data set. And it's called a Moon data set because it's just kind of two half moons. So here you have an orange moon and a blue moon. And so that's our regularization. And so we have parameter x1, we have parameter x2, and then the class that we're going for here is the orange and the blue. So those are our two different classes. So relatively straightforward. And here we have absolutely no restrictions, right? And you'll see a model that wants to classify those 2 points. So while that is technically correct, in that it correctly classified those 2 orange points, I think anyone who looks at that model would say that those should not be, that's an overclassified. It's also pulling out this orange one. So this model here doesn't do quite as well, but is a much better model and is definitely less overfit. Something to think about in terms of decision trees is their computational complexity. And so when making a decision with the decision tree, that involves transferring from the root to the leaf, right? And so they're generally well balanced. So the root to the leaf approximately comes out as O to the log 2 of M. So since checking the node involves examining just one feature, the overall complexity for making a prediction is only O to the log 2 of M, making it exceptionally fast, right, regardless of the features. So it actually scales very well. You can have 1,000 features, but because you only have to check one feature at a time, you can make your precisions very fast. Training is more intensive and depends on the number of max features. So your training complexity, could be O to the N times M log M, where N is your number of features and M is your number of samples. And so that can actually get and become a more complicated or more expensive to train than it is to infer. So something to think about when you're training, but really overall, it's not too bad. So there is more than one way to figure out which model you want to use to, or which cost function you want to use to train your models. You can also look at entropy. Kind of versus a Gini or Gini impurity. So entropy kind of originally comes from thermodynamics, which is something that, as someone from an engineering background, you might appreciate. And so our goal here is that entropy reaches zero, and when the molecules are the complete state of rest and order. So that concept can be adapted to information theory. It's kind of the famous thing that Shannon did in the Shannon information theory, while also defining bandwidth. In the realm of machine learning, entropy serves as a measure of impurity. It is zero in a data set where all of the elements belong to one class, right? So we're trying to get to one element. So the entropy for the ith node is h of I is equal to negative summation of n over k equals 1 of pi comma k log of pi comma k. So the choice of entropy and Gini is kind of a personal choice. Really, they don't produce very different results. Gini can be slightly more computationally effective, and so is the default choice in scikit-learn. However, it does tend to separate most frequent classes into distinct branches, whereas entropy generates a more balanced tree. But the end results aren't a lot great, or aren't a lot much better. Really, one of the key reasons to use entropy is to use it along with Gini in a random forest, and that way you have two types of trees in your forest, right? Gives you a more diverse canopy, which maybe makes things a little bit more robust. So not bad to use, but it's not going to be a game changer. But you should absolutely know kind of what the difference between entropy and Gini are.